Hello, I'm Marito, and welcome to the Cram Podcast. Well, do you ever jokingly use the term black hole? Like, my inbox is a black hole. Things go in and never come out. Or, my mind is a black hole. Stuff goes in, but it's lost forever. We may joke about black holes, but they are not to be trifled with. They're the juggernauts of our universe. For example, Sagittarius A star, the supermassive black hole at the center of our galaxy, the Milky Way, is over 4 million times the mass of the sun, with many mysteries still to be explained. And one of the researchers who's passionate about finding more answers to black holes is astronomer Daryl Haggard. She's an associate professor of physics at the Trottier Space Institute at McGill University. She's also the co-leader of the AXIS mission, a space probe that aims to increase our understanding of black holes and the evolution of our galaxies. AXIS is one of 2 finalists in the NASA $1 billion space probe competition, and Daryl joins us. Hello, Daryl.
Hello.
Well, first of all, congratulations. That is amazing. Tell me what your reaction was when you found out you were one of 2 finalists at this NASA competition.
Yeah, so it's pretty exciting. I work in a big team. I'm a very excited member, and as you said, a co-lead of one of the primary working groups, but it's a big team and people were thrilled. So of course, the moment you find out, it's just a flurry of emails and Slack messages and enthusiasm. So, these are very competitive calls. The competition is excellent. Everyone is so fantastic. Every mission is beautiful. And so it's pretty exciting to have yours get kind of pulled up out of the pool.
Now, I want to get into black holes because I started talking about them in the introduction, and I know they're one of your things. But from what I understand, you were originally a philosophy major. Is that right?
That is true. Indeed. I did my undergraduate degree in classics, in great books, at a very small college called St. John's. And believe it or not, I actually got excited about astrophysics in that program. I was studying Newton's Principia, and my professor was teaching us about how you can actually slingshot spacecraft off the gravitational fields of planets. And I was like, what? That is so cool. Anyway, so that's part of my sort of origin story of how I got really excited about pursuing astrophysics as a career.
So regarding black holes, I think, many of us have heard about black holes and we love seeing them depicted in science fiction movies. But why don't we start off and you just explain to us what are black holes?
Okay, I'm going to give a very simplistic, but I think very illustrative definition. So here's my favorite description. If you imagine that Daryl is a regular person, she goes outside, she throws a baseball, and we all know what's going to happen. Daryl's baseball is going to fly through the air and crash to the ground. I don't have a very strong throwing arm. It probably won't go very far. Even if I am Wonder Woman, I probably can't throw the baseball hard enough to launch it into orbit, or maybe I can. But it turns out that to get a baseball into orbit around our Earth, you have to throw it at 11 kilometers per second. That's actually pretty fast. And if you do that, you can actually send that little baseball into orbit around the Earth. And if I throw it a little faster, I can get it out of the Earth's gravitational field. So remember that number, 11 kilometers per second. This is what it would take to send out a telecommunications satellite and get it out up above the Earth's gravitational field. So in a black hole, you have mass so densely packed, so much mass in such a small space that velocity, that characteristic velocity, which we call an escape velocity, is faster than the speed of light. So a photon is the baseball. A photon is trapped in the same way that Daryl's crappy throwing arm cannot give it enough speed, enough velocity for it to be able to escape the gravitational pull of the black hole. And as a result, since light carries everything. That speed of light is kind of our cosmic, speed limit. We don't know how to send any information faster than that. That means if the photons and the light is trapped in the black hole, everything is trapped in the black hole. all the information, all the mass, all the photons, everything. So I love
Everything that
this.
gets, yeah.
Go ahead.
Sorry, can I just clarify? So you're saying everything that gets like trapped or sucked into a black hole stays there.
That's right. It can't come back out. Yeah.
It can't come back out.
So when you think about like eating breakfast or something, right, you put a bunch of energy in and then you burn it up through the day and that comes out as heat and, you know, makes your muscles work and whatever. You put stuff into a black hole and it's trapped in there. Like it doesn't come back out. Once it's crossed over the event horizon, it's gone forever.
Right.
We don't ever see it again. And that's true of everything.
Stop.
Yeah.
Stop. You said event horizon. What is that?
Yes. So the event horizon is actually the surface. So black holes are a 3D object. So the event horizon is a 3D surface that is basically defined by this little definition we just came up with for black holes. Once you are within the vicinity where the escape velocity is faster than the speed of light, you are inside the event horizon. So it sort of is this notion where you have now trapped material inside that black hole and it's passed over the edge, passed through that point of no return. There's a more formal way of deriving that. It has to do with, you know, cosmic space-time continua, but it's basically this concept that once you have this sort of enough mass packed into enough of a small space, you can actually create this sort of bubble that is the event horizon, and stuff is trapped once it passes that boundary.
How did we get that black hole in the first place?
Great question. So it's hard actually to make a black hole. It takes a lot of stuff. So I can tell you, I'll give you again a sort of a simple example. The black holes that we think we understand the best come from stars. They have to be stars that are a little more massive than our own sun. But if you imagine a star that has maybe 40 or 50 times the mass of our own sun, the way that the stars stay stable over long periods of time is that they burn fuel in the inside. And people, I think many people will know this, they fuse together hydrogen into helium. It's a fusion process that generates a lot of energy. So the basic principle of a star is a balance between energy being made in the inside and pushing out in the form of photons and heat, and gravity pushing down. And the star is stable as long as those two are perfectly balanced. We call this hydrostatic equilibrium is the fancy word, but it is basically a balance between gravity pushing in and fusion reactions making energy to push back out. When you run out of stuff to burn, when you don't have hydrogen to fuse anymore, gravity starts to win and pushes stuff denser and denser and denser. So then you make another dense element. You can burn that for a little while, but it's kind of a runaway process. It's really hard for the star to recapture that equilibrium. So once it runs out of hydrogen in the core parts of the star, gravity just starts to crush all that stuff down in there, and it burns and it burns and it burns and it gasps and it tries to stay alive, and eventually gravity wins. So weird things happen after that. So eventually what you get is actually, you know how electrons have negative charge, and when you try to push two negative charges together, they resist. So the next thing that happens is that electrons actually push back against gravity and hold up the core of the star. All those little tiny electrons are like, no, please don't crush me. And they push back and they hold the star up for a little while. But if you have enough mass pushing down, gravity is just relentless and it pushes and pushes and pushes. Eventually the electrons can't hold it up anymore, and the electron gets shoved down into the proton and makes a neutron. And then sometimes the neutrons can push back against one another and hold it up. But if you have enough mass and enough gravity pushing it down, eventually the neutrons collapse, and we don't know. Like, we actually can't make a neutron sauce like we have in the middles of stars and see what happens after you exceed their ability to fight back. And that becomes a black hole. Basically, there's nothing to resist gravity, and everything just crushes down to this extremely dense material. And we can't build it in the lab, so we can only study it indirectly through astrophysics. And meanwhile, I said at the beginning of this that it's a supernova. So meanwhile, all the stuff on the outside is sort of like, whoa. And it actually a lot of the stuff actually kind of bounces off the surface of that very dense stuff and makes a supernova explosion. So we do see the supernova explosion. And then in the center left over is a black hole. Maybe that was a kind of complicated explanation.
No. I mean, I'm going to just assume that I understood most of it, but I think I understood the basic. I think I understood what I need to understand. So what I'm wondering then is, if gravity is such a phenomenal force, right, that it can overpower the electrons, then the protons, then the neutrons, right? After all that happens, is gravity still pushing down and making it denser and denser? Is that process infinite, is what I'm asking.
We think so. It's not clear.
Really?
Okay. There might be something else. So there could be another source of resistance or pressure, something that pushes back after you've overcome these neutrons that are trying to hold themselves up. And our understanding of how those neutrons work really comes from quantum mechanics. So, astrophysics and quantum mechanics really developed together quite a bit in the last century or so. And so it is possible something else takes place, but because no information comes out of a black hole, we don't have any way to test what's happening.
Yeah.
So we have a lot of ideas, but when you run out of ways to test something, you start to tiptoe into the land of a kind of a philosophical, very theoretical imagining of what could happen, but it's difficult to test it.
Well, see, that's the other thing. I guess there must be theories, right, about what happens to the information, like the mass that's within the black hole.
Yeah.
I mean, what do you think? What do you think happens to that? It's constantly getting denser and denser and denser. Does it disappear? Is it still there?
I think it's still there.
You know what? You think it's still there? Do some people think it's not there? Do some people think wormholes, other universes, pathways into other universes or something. I'm a totally practical person. I'm like, that stuff's still there. I can tell you why I still think it's there. The reason I believe Daryl believes it is there is because, once again, I am a total empiricist. I am like the boring mom of scientists. When I look at a black hole, what I am looking at as a scientist usually is its influence on its surroundings. And so you mentioned in your introduction, Sagittarius A star, the supermassive black hole in the middle of the galaxy. That black hole, and the reason we know it has 4 million times the mass of our sun, is because that black hole acts like a 4 million solar mass object. Things orbit it. Mass falls onto it. It behaves exactly like any other astrophysical object that has gravity. So to me, that means the mass is there, because a star that comes near it orbits around it, just like our planets orbit around our sun. They treat it just exactly like all other mass. So to me, that means the mass is there. What it's doing in there is a completely other question. It's in a state of kind of a state of matter that we don't have much knowledge about. And do black holes follow the principle that matter cannot be created or destroyed?
We think so. I mean, everybody wants to break these theories, right? It's fun to break theories. You learn something new. But we have never seen evidence that the black hole is, in some way, destroying matter in some kind of fundamental way. We think it's the same physics, and general relativity tells us it should be the same physics. And every time we try to break relativity or figure out if we've seen relativity be violated, it just gets validated every time. So it's very exciting to try to break it, but it hasn't broken yet.
And then, okay, so you know how, and I think we mentioned this earlier, how a black hole will suck things into it, right? It can suck matter. Oh, not suck. Sorry, it falls into it. I don't know, what's the word? It falls into it.
Right.
Does it fall into it?
Perfect. Okay. Yes, I have a whole public lecture
falls into it.
Yeah, I have a whole public lecture that's called Black Holes Don't Suck, which makes everyone laugh.
Oh,
And I can get the entire audience being like, black holes don't suck. Yeah, so it falls in. But it doesn't.
Falls in. Okay.
Yeah, there's no sucking.
So, all right. So then you mentioned that other stars will orbit this black hole.
Yeah.
Why don't they fall in? Like, what determines what falls into a black hole?
That's a great question. So why doesn't our Earth fall into our sun? Just because they're stable, it's a very fabulous and totally mind-bending thing that bodies free floating in space can just stably orbit one another. If nothing comes along and bumps into anything, we just do that forever. Like, it's incredible, right? And so stars outside of black holes are just like our planets orbiting our Earth. They follow Keplerian dynamics. They orbit in behaved ways. But then if you want stuff to fall in, what you have to do is you have to steal a little bit of energy away from the star. And if you steal a little bit of energy away, it'll slowly get to a lower orbit. And if you steal a little more energy, it'll get to a lower orbit. And if you steal a little more energy, okay, so then how do you steal the energy? You can steal the energy by having a lot of like gas and dust. So the star is kind of plowing through stuff. And as it plows through stuff, it loses a little bit of its momentum and it falls in a little bit. You can also sometimes have an interaction between the black hole and the star that kind of stretches it out. And if it stretches out a little bit, that makes it heat up. And so that makes it lose a little bit of energy. So if you want something to fall into the black hole, it has to have a way of shedding a little bit of energy away. And slowly its orbit will decay and it will fall in, just like a meteorite will fall to the Earth. It doesn't have to do that. But
yeah, that's okay. Is this, I don't know what to call it, behavior of the black hole? Is it intentional? That it wants to suck the... Oh, it's not.
I don't think so.
It's not intentional.
No, I mean, black holes are perfectly happy to have stars orbit them stably. So for example, once again, to remind you, you said our black hole in the middle of the Milky Way galaxy has slightly over 4 million times the mass of our sun. Why do we know that? We know that because we can watch stars orbit around the black hole. We can watch 20 stars orbit stably around the black hole. And we know, just using very simple Keplerian physics, we know how massive the object has to be to keep those stars stably orbiting. But the black hole doesn't care if they don't fall in. The black hole is perfectly happy for them to stay there and orbit around and do their thing.
So then what triggers then something going into the black hole? Like, why? Why would that even happen?
Yeah. So imagine now that you have a black hole and 20 stars orbiting around it. And just imagine like kids on a playground. Like every time those stars go by each other, they gravitationally interact a little bit. They nudge each other a little bit and they change each other's energy. So the system can become chaotic. Things can kind of shed a little bit of energy as they kind of gravitationally bounce around in there. And if you get enough energy out of the system, then something will start to fall in and it will start to get sheared out. We have a great word for that. It's called spaghettification. So a star will eventually get spaghettified, turned into spaghetti. Stellar spaghetti. Okay. And so what happens, and the reason something gets spaghettified is if you're coming close to a black hole and a little bit of the mass is slightly closer to the black hole, it gets slightly, a little bit more of a gravitational tug than the thing that's farther away. And then that gets a little bit closer and the thing that's further away gets a little less. And like slowly but surely something gets stretched out. So stars will eventually, if they're in an environment where they get kicks or bumps or something else comes flying in from, somewhere else, they can actually be sort of disturbed or disrupted and eventually fall in. And the other thing that falls in, so I don't mean to make it sound like black holes don't grow. They do grow. They do have mass and stars and things fall in. The other thing that falls in is a lot of gas and dust. And gas and dust is constantly, it's much more interacty than stars. So it's like rubbing up against other gas and dust. And so it actually loses energy much more easily because it heats up as it gets kind of, more and more interaction with other gas and dust. And that heating causes it to lose energy, and that loss of energy causes it to fall in. So gas and dust fall very efficiently into black holes, or more efficiently than stars.
But it's not like, do we know it's not as if black holes need stuff to fall in? Like if nothing ever fell in, that's okay. They're still hanging around.
Yeah, they're hanging around. They're like trees. They're like doing their thing. They grow. They absorb carbon. They get big, but they don't. Do
they ever die? Do they ever disappear?
Oh, that's a good question. So big ones, not in the age of our universe. Very tiny black holes might evaporate, is what we would call. That's how they would disappear. And so this is, again, a little bit hard to explain, but we have this idea that, and this is an unproven idea. This is an unproven idea that Stephen Hawking put out there into the world and that people love. It's called Hawking radiation, but we have never observed it. So I will describe it, but just know that this is a theoretical idea. It's a notion, but not something that we have seen.
Right.
So the idea is that because of quantum mechanics, in vacuum, so in places where there are no particles, vacuum actually has the ability to kind of pop to, like a particle and an antiparticle can pop into existence, and then they can also annihilate and go back out of existence, which sounds crazy. It's kind of like matter appearing and then disappearing. And that works, and it stays vacuum if you have exactly the same number of particles and antiparticles. And so we think this can happen. And if you imagine that you're in empty space next to a black hole, and a particle and an antiparticle appear, and one of them falls across the event horizon, now it can't recombine and go back to being nothing. And it carries the one that doesn't fall across the event horizon, carries a little bit of energy away, and sort of indirectly saps energy out of the black hole, and sort of slowly can evaporate, but only a very tiny black hole, like one that's like almost like microscopic. This process would be extremely slow, and it would take way longer than the age of the universe for even a teeny tiny black hole to evaporate.
Okay, so I'm going to be honest. I didn't really understand that when you get into things like going back to nothing. That's a phrase I'll have to think about, going back to nothing. But okay, let me ask you this though.
Totally fine.
I'm not going to sleep tonight. I want you to know that, Daryl.
I know you're going to be like, is the vacuum coming for me?
Okay, so the thing is though, when you say evaporate, right? To me, that sounds as if it's turning into nothing. Like what happened to that something, which was the black, that even if it's small, it's still there. It's a black hole. Then you say it evaporates. Well, it evaporates into what? Like what?
Yes.
What happened? Like, where is it? What's going on?
Fabulous question. Okay. So this is another, like, you're asking all these like really fundamental physics questions.
Okay.
Like they are deep questions, and they are not really intuitive, to be frank. So one of the things that Einstein's theory of general relativity tells us is that matter and energy are equivalent. And you've seen this equation 1,000 times. It's E equals mc squared.
Right.
Right. And that c squared, that's this, speed of light thing that is like a constant speed. But what that equation is basically telling you is that energy and mass are the same thing. The speed of light is just like a constant, so you don't have to worry about that. So that energy mass equivalence means if I take energy out of a system, that is exactly the same as taking mass out of a system. So when I told you these two little particles are near the horizon and one of them carries away energy, it is carrying away the black hole's mass. And it just took it away as energy, not as mass. And so you know this. You've seen E equals mc squared 100 times. You just didn't believe it profoundly. Like energy and mass are literally the same thing. But that is what that black hole evaporation idea is really leaning into, is that those are the same fundamental thing.
Let me ask you, because as I said, I'm not going to sleep tonight. I'd like to know what keeps you up at night about black holes. You know what I mean? What really gets to you? What really bugs you, like about
bugs me about black holes?
Yeah, like you're just I gotta get I got to find out what's the conundrum, right?
The first thing that came to my mind was like my teenage son keeps me up at night. What keeps me up at night about black holes? Okay, I can tell you one thing. Well, there's two things I can tell you that we just try as we might, and we have tried, we cannot figure out.
Okay.
There are two, I'll tell you two different things.
I'll try my best. I'll try my best. Go ahead.
Yeah. Oh no, you'll understand these for sure. So here's two things. Okay, I told you how a black hole forms through an exploding star.
Yeah.
I did not tell you how a 4 million solar mass object could live in the center of our galaxy. An exploding star makes a black hole that is sort of about the same mass as the star. And I told you the star had 40, not 4 million times the mass of our sun. So the black hole it makes is going to have something less than 40. So I can go out and look at the universe, and I can see a lot of black holes that have masses that are like 10, 20, 40, maybe even 100 times the mass of our sun. And I can go out in the universe and I can find a ton of black holes sitting in the middle of galaxies that have millions or billions of the times the mass of our sun. But I can't find anything in between. There's nothing that's 1,000. There's nothing that's 10,000. I'm exaggerating a little bit. We know of a few, but like, why do we have little ones and big ones and nothing in between? Especially because it would be tempting to think that you start with the little ones and you grow into the big ones. It's almost like if we had toddlers and grown-ups and no teenagers. Like they're totally different populations. Like, how do you get from one to the other? Why don't you have anything in the middle? Like, what prevents you from making teenagers? So this is a very strange thing.
Yeah. And are you telling me, do we know whether those mid-sized, I don't know what to call them, but teenager black holes, do you know whether they never existed or did they actually exist at one time?
We don't know. That is a great question.
You don't know. Okay.
Astronomers don't know. We can find a few. I don't mean to totally exaggerate. Like, we can find a couple, but like I can find you thousands of the little ones and millions of the big ones and like a few of the ones in the middle. Like, and it seems like if you think about any kind of population and you think about things evolving from one thing into another thing, that you'd find just as many in the middle. And we don't. So this is a great puzzlement to astronomers. We have looked, we have tried, and we don't call them teenager black holes. We call them something more mundane. We call them intermediate mass black holes.
Oh, that's so boring.
So boring. You can always think of them from now on as teenager black holes.
Although I will say, I don't know whoever named the big black holes supermassive, but I find that a bit overdone.
So I'm sure somebody was just like, what? Like, it's not, why is it so massive? Okay. So that is one mystery that myself and other astronomers are very puzzled by.
Okay. Woo. All right. What's the next one?
Yeah.
What's the next one that keeps you up?
The next one.
Yes.
Yeah. The next one is related, and you already know it now because I've kind of told you, but like, we really don't know how you make supermassive black holes. Like, I told you how we make the ones that come from supernovae. And I have never told you how we make the ones that have 1 million or 1 billion times, because we don't know, times the mass of our sun. And the weird thing about the supermassive ones is that it appears that one of them sits at the heart of every galaxy, at least every massive galaxy, and that they form very early in the universe, like very early. So when we look back with our telescopes back toward the Big Bang, as far as deep as we can see, we see supermassive black holes. So like they're there at the beginning, and we don't know how they form, because what I explained to you is, here's a thing, I throw gas, I throw stars, right? So, but like, I'm throwing stars, like a star is 1 times the mass of our sun, or maybe 50 times the mass of our sun, but it would take billions of stars to make something that is a billion times the mass of our sun. And we don't see things with like billions of stars flying into them. So how do you make them so big? And how do you make them so big so early in the universe?
Right.
And the reason this is an extra puzzle is that you might say, well, gas, I told you gas is really good at getting in there. And that's true. So maybe you just shove so much gas in there so fast at a very early time in the universe that you just build the black hole really quickly. So that's possible, except that when you throw a lot of gas in, it heats up and it starts to do exactly what I was telling you about stars. The heat starts to push back against the material. And so you effectively shut off the process that pushes the mass into the black hole because you're generating so many photons, so much heat that you kind of halt the infall. And so it becomes really difficult to build a supermassive black hole. And so people have crazy ideas where they're like, well, if you're really in the universe hasn't seen any supernova yet. And all it is just pure hydrogen gas. So maybe it just gets a little bit dense and then just collapses straight into a black hole. And you're like, okay.
I don't think you buy that. I can tell you don't buy that one. Yeah, I could see that. I can see that.
No, I think it's the winning theory right now. It's called direct collapse. You just you just make it. But yeah, we're still trying to work it out.
No, I can hear the skepticism in your voice. I can hear the skepticism in your voice, Daryl. Yeah.
Anyway, those are two big questions.
Those are amazing. I feel almost stupid asking this question, but I'm going to ask it anyway. Okay. Well, the fact that you said, okay, first of all, let me just clarify one thing. You know, when we were talking about Sagittarius A star, right? The one that's at the center of our Milky Way. Okay. So that is a supermassive black hole, right?
Black hole.
Are you telling me then that was not created from a star, right?
Nope.
Okay. It wasn't. Okay, so
that's unlikely.
Right. That's an example of what you're talking about. So if you have so many of these super massive black holes at the beginning of, time, so to speak, right? Very close to the Big Bang. Early on. Is it possible that they all resulted from the Big Bang? That's why they were there?
No, probably not. So we have a lot of complicated theories about what, the whole field of cosmology is really preoccupied with understanding how all of this stuff worked at the very first moments of the universe. So at the Big Bang, we do see really interesting fluctuations. You could talk to a whole other wonderful set of scientists about these, but everything was super hot, very small. And there were little tiny fluctuations. And then the universe underwent this huge expansion, which we call the Big Bang. And those little tiny fluctuations are imprinted on our universe. We actually do see, like, where there were little fluctuations up, we see slightly more mass. And where there were fluctuations down, we see slightly less mass. Galaxies, big, huge structures, like big groups of galaxies and black holes and things have settled into those slight over densities and under densities, but they're on huge scales, like really enormous scales compared to the ones that we're talking about where black holes are. The physical size scales are much larger. Also, the universe has gone through many times where like all of the material was, ionized, where all the electrons were stripped from protons, and then it, they recombined. Like we've gone through, there's all this kind of complicated story that we tell ourselves as scientists that we think match our data. And the black holes and the galaxies are a little bit closer to us in time than all of that interesting early universe stuff.
Okay.
So,
this is just so interesting. It makes me wonder too, like all these actions that happen in the universe. So, on Earth, right, we have different ecosystems and how things are in balance. And then you change one thing and it could affect the whole ecosystem, right? And one species, let's say, goes extinct and then, that has a ripple effect. So I'm just wondering, like with the universe, is there actually a balance or stability to it or some kind of pattern that you can identify?
Yeah.
Yeah.
Yeah, I mean, I think, to be a little philosophical about it, I think that is exactly physics. The balance is exactly what we understand to be physics, right? That's all those laws that we pull out, like E equals mc squared and Kepler's laws. They're all our best shot at describing that balance or imbalance when things are changing quickly. Thermodynamics is all about how things are going to change when they're in contact with one another. And so I think there, to the extent that this is what we seek when we are physicists looking for an explanation, it is to describe that, exactly what you're talking about. And one thing that I think is a sort of an illness of us as a field is our desire for that simplicity rather than that complexity. So you started talking about ecosystems, and I thought you were going to go one way with that question. But physics is really about the reductionist kind of description of the underlying balance of things, where I think as scientists, we're learning more and moving more toward that kind of ecologist's complexity, because we realize our reductionist ideas aren't enough. They can't tell us enough about all the weird things that are happening that allow that gas to fall into that black hole. Our simple ideas are too simple. They don't give us enough leverage. We can't actually create in our computers and in our theories the universe we see. So we know we're missing something. And I think that's actually leading us more toward complexity. But we still are very attracted to the beautiful ideas. The simple ideas are very compelling, but they sometimes aren't quite enough.
Yeah. Yeah. Well, simple minds, simple ideas. We like that.
I know. We do. Yeah. I do.
Yeah. Well, exactly. Well, you could take that whole idea anywhere, politics, whatever, know?
Yes.
So, yeah. Okay. So, did you start as a mathematician?
I mean, I think kind of in some ways we're all mathematicians, all of us who do the physical sciences. Yeah. I mean, we certainly do a lot of math. I loved math when I was young.
So I want to ask you, because I think, when I didn't really know anything about astronomy or the field or whatever, I just assumed that astronomers saw what they were talking about. But how much do you actually see? Like everything you talked about so far, everything you described to me, how much of that have you actually seen?
Well, that's a good question. So I would say we are learning to see more and more things. So, I work with a group called the Event Horizon Telescope, and this group has given you the orange donut of the black hole image. You've probably seen it. That is our very first picture of some of the things you and I have talked about.
Yeah, just to clarify, sorry, is that the image from 2019? The very first image of the...
Yes.
Yes. Okay. Yes. The black hole. Okay.
Yeah. And so that image is really a spectacular image, and it is literally showing us a picture of some of the things that I've told you. So gas and dust, in the vicinity, just outside of the event horizon, losing energy. That's why we can take a picture of it. It's emitting photons. And as it loses energy, it is falling close to the event horizon and soon going to fall across the event horizon. And so, to an empirical person like me, it is really exactly an image of that process. And, the wonderful Nobel Prize that happened, I don't exactly remember what year, it might have been 2020, could have even been 2019, was actually given to scientists who studied those stars I keep talking about that are in orbit around the black hole in the middle of our galaxy. And they really take pictures of those stars and movies of those stars orbiting around the black hole. So to some extent, some parts of the things I've told you, we are observing directly. We see them directly. Other things we use, we infer the existence of the process or the thing. So I told you about how fusion occurs in the core of a star. So I can't go into the the core of the star. So I can't exactly observe that directly, but I can make a very concrete prediction about what should come out at the surface of the star if I have correctly described what's happening on the inside. So I do have a beautiful measurement of what's coming out at the surface, and it validates the theory I have about what's happening in the center. So it is a little more indirect in that way. But we see a lot. We can see a lot, and we infer a lot. We guess a lot.
Yeah.
And we just try to make our guesses better and better, and then design our observatories and our questions better and better, so that we're more and more confident that the thing that we can't see, is actually described by our theory.
So that brings us back to Axis, because I want to end off talking about that. Yeah. So tell me, like, what the purpose of that mission is. Because now, let's see, you've got a year to work on it further, right? Before they announce, I guess, who is the lucky, team that their project is going to be realized in 2026. So, so tell me about Axis.
Yeah. So Axis is an X-ray observatory. And what that means is that it is specifically optimized to see very energetic photons. So things that are very, very high energy. And all of us, we have the advantage of understanding X-rays at least a little bit. And that's because we've all seen an X-ray of our hand, or, when somebody breaks their leg or whatever. And the reason that helps you understand X-ray astronomy is that the way you take that picture is you're actually shooting high energy X-rays through, say, my hand right now, and it gets stopped by my bones, but it passes through all of my tissues. And so what I see on the image, if I have like a film back behind here, some sort of photographic film, is all the places where the X-rays couldn't get through because they were stopped by my bones. And so what that tells you, though, is that X-rays are really successful at passing through all of the tissue, all of the less dense stuff. And that makes X-rays really powerful for studying the universe, because it means they can pass through dust and gas and get out of things that they might otherwise interact with more. So they're photons that manage to penetrate through dense material and travel unimpeded for us to look at them and understand, what system they came from. So they're very powerful in this sort of interesting way, that they're just very successful at, kind of shooting through other material and not being absorbed or blocked or redirected. So this is true of most high energy emission. So then you ask, okay, that's great. So what do they actually show you? What they show you are the hottest things, explosions, those photons really close to the black hole. You need these photons to be very energetic. So an X-ray photon, when it's created, comes from a very energetic process. So a lot of times it could be like, things smashing together, or one thing colliding with another thing, or some, a supernova explosion, a star exploding, or in the case of the thing we've spent most of our time talking about, when you have material fall very close to that event horizon, as it gets close in there, it gets hotter and hotter and hotter and hotter. And eventually, when you're really close to the event horizon, the heat, the energy that's being lost by those particles are often X-rays. So X-rays are really good at showing us the environments really close to the black hole, or supernova explosions, any kind of a cool, exotic, explosive things. So Axis is an observatory that's designed to go after this very energetic, very hot, very explosive universe, or very, just like kind of like really, really hot environments like black holes, the vicinity just outside the black hole. So Axis is going to be at this amazing observatory that looks deep back in time at those supermassive black holes we were talking about, tries to figure out like how'd they get there, why are there so many, and how fast are they growing, and what's going on?
So wait a second. So are you saying that if you're able to get this observatory, you may be able to answer those two questions that are keeping you up at night?
Well, at least one of them, yes. Well,
Oh,
I mean, we always hope that. Otherwise, we wouldn't, want the observatory. But yes, in connection with like a lot of other observatories, you need lots of puzzle pieces. But yes, I mean, yes, absolutely. That is one of the fundamental questions that we are trying to answer is how do you build those big things so soon? And how many are really there? And when did they start? So
okay.
Axis is for sure going to tackle questions like that.
And okay, am I to assume that the technology behind Axis has not been realized yet? That's what this money is going towards, or you do have the capability already?
We do have the capability. So yeah, every space mission sort of, rests on the shoulders of giants. So we currently have an amazing X-ray observatory, which is called the Chandra X-ray Observatory,
right,
which I have built most of my career on. It has been, I always tell people I launched the same year that Chandra did in 1999. I started my master's degree, and that's when Chandra went up in the space shuttle. I'm actually currently at a conference where I got to meet all the astronauts that launched Chandra.
How exciting.
So that was like, very cool. I was in the elevator with an astronaut the other day. Katie Coleman, she's like super fantastic.
Wow.
So Chandra has been up for 25 years. We are having a 25th anniversary party right now. And it is very good at detecting these X-ray photons. But it is getting a little bit older, and, it has different capabilities than Axis. So Chandra is very, very good at pinpointing things, but it can't see a big area all at once. Axis can actually take observations over a large area all at once. And so when you're trying to do a survey, like a demographic survey, we were talking about looking for teenager black holes. It's nice to be able to look for, across a larger field, all at the same time. To 25 years sees a lot of technology development. We'll have some new ideas about how to do the science. Also, one of the other things I study is actually exploding things. So when you take two dense stars and smash them together, they make a big explosion. And so Axis is very agile. It's very quick. So it can move across the sky and go and say, oh, something just happened over there, and move over there very rapidly, where our current observatory is much more massive, much harder to move rapidly. So every observatory sort of uses some of the technology legacy of the previous one, and then tries to build in new features to kind of optimize solving these kind of fascinating science questions.
What, because, people listening to this, they may think, oh, okay, this is all fascinating stuff, but in the end, what will it mean to me? Like, what will it mean to me here on Earth, to us humans? What?
Yeah. I mean, I do think, any kind of pure research is very curiosity driven. So it is, what is our place? How do we get here? Why does our galaxy look like this? Why does it act like this? Why does it have a black hole in the middle? So there are some of these more, I guess they're a little more whimsical or curiosity driven, some of those questions. But then there are a lot of things that we've learned. There's a couple of different ways to cut that question, but I'll tell you one. So I was just talking about stars colliding together. So supernova explosions, where a star explodes, or collisions of stars where they explode, synthesize heavy elements. So in fact, almost the entire bottom half of the periodic table comes from stellar explosions. So like all of the iron in your blood came from a stellar explosion. So to some extent, it's not just about like the origins of our universe, it's our very own origins. Like, where did our chemistry come from? You can't build planets without having all of these heavy elements seeded into the system from these explosions. So we want to understand, how did the explosions progress? How did they make those elements? How did those elements make it to our planet to leave us with, enough iron to build all of these bodies? And it has a very practical and almost profound kind of circle of life thing. If you want to understand really where our biology arises from, you actually really have to look to the stars, because that's where it started. And if you don't have that, you're not going to know exactly, how general our chemistry is, how general this
Mm-hmm.
periodic table is. Is it the same imprinted everywhere? Is it in some way unique? Is our environment generic or unusual? And then I will just say the last, much more practical thing is that an enormous amount of our technology was driven by these kinds of curiosity pursuits. Astronomy gave us these crazy widget cell phones we carry around. I mean, all of those little CCD cameras, those were developed in the service of doing science. And so we drive a lot of technology development. Axis is a fantastic example of that, developing these like very unusual optical systems to bounce X-rays around and focus them onto a chip. We really work hard on the technology development that has all these kind of tack-on effects that end up in everyone's pocket. Just kind of cool, kind of weird.
Yeah, totally. Oh, I love it. I love it how we went from supermassive to right in your pocket. There's a direct connection, right?
Exactly.
This was
and all those elements in your cell phone also came from stars.
Right. Yeah, no, I love that connection. Oh my gosh, Daryl, I could talk to you forever. Yeah, forever, infinity. This was great. I can't even imagine how exciting this year ahead is going to be for you.
It is.
Yeah,
it really
so
is.
I wish you and your team all the best, and we look forward to hearing what's next for you and everyone.
Great.
Yeah, thank you.
Thank you very much, Mary. It was a pleasure.
That's Daryl Haggard. She is an astronomer, associate professor of physics at McGill University at the Trottier Space Institute, and she is the co-leader of the Axis mission, and Axis is one of two finalists in the NASA $1 billion space probe competition. And of course, the winner is going to be announced in 2026. Well, we hope you enjoyed today's podcast and all our podcasts. It's hard to believe that we started this over 3 years ago, and our team has loved bringing you CRAM and all the latest research. Research is vital. That's how we make advances in our lives. But so little is known about Canadian research, and that's, of course, why we bring you CRAM. We are reaching out now, though, to ask you for a donation to keep it going. CRAM is a charity, and for those donating from Canada, you will receive a tax receipt for your contribution. You'll find the link in our show notes, as well as a donate button on our website, cramideas.com. Thank you so much for supporting us and the exciting research and big ideas of Canadian researchers. We truly appreciate it.